It is good to be here. I've probably been to this conference more than any other in terms of dairy production conferences, and it's one of the best in terms of actually science that's presented and interaction with producers. And I can say over the years I've had the best interaction with producers or nutritionists at this meeting any place I've ever been at. So congratulations to Professor Santos and Staples and whoever else is involved in that. You've done a great job over the years in that. And I think is Charlie still in as he stepped out? I'm going to pick on Charlie. I had a bit of a Laurel and Hardy moment getting ready to come up here. And I got an email from Charlie's office, and it said, the office said, what do you want to be listed as? And I emailed back and I said, after 30 years I've retired from university. I don't care. And I got an email back and said, oh, that's funny. Really, do you want to be put as a retired emeritus or what? And I said, after 30 years, I don't care. And I got another email back, said, how about if we put down emeritus? And I said, no, I really meant I don't care anymore. Just put that down. And so I think Charlie saw that, because I'm picking on him because we were in grad school together. He was quite a bit older than I was. I just want to point that out. But we were in grad school together. And when I got here, I went to registration desk. I picked up my badge, and it said consultant. Now think about that, those of you who are consultants. You're a retired university professor, and somebody just labeled you that you can work like a consultant. I broke out in a nervous sweat for about 2 hours after I got that badge, thinking what that, and I'm putting that all on Charlie's shoulders. Charlie was laughing about that when he did that, I think. I want to start on these slides now, and the other preface I would make is I took some decongestant. So each time a slide comes up, it's as much a surprise to me as it's going to be to you. All right, so I'm going to try and get through them. So the other speakers this morning, I think, have made a case about the importance of amino acids and thinking about that nutrition of these ruminants. I think a lot of the limitations of that has been how we estimate or predict amino acid flow from the microbial fraction. That's something we spend a fair amount of time on. We've used that then. I think we can be fairly accurate in predicting what amino acid flow post-rumally is from the bugs. We've used that and did most of our work in milk in efficiency of growing cattle. After you spend about 15 years working in beef cattle and you get something that works, you look at the results and you say, why in the world didn't I start this in dairy cattle instead of beef cattle? Because it makes more sense in dairy cattle than it does beef cattle. And in beef nutrition, I'm a little tongue-in-cheek, but in beef nutrition, it's hard for us to even spell amino acids, much less think about it in formulations. So all the work we've done has been in beef, and I'm going to use a couple of slides to show the importance of that in cattle. The other thing to preface this talk is if I went into a group of beef producers, Randy, you tell me if I'm wrong about this, if I go into a group of beef producers and I ask them what's the most important thing you want to improve in these calves in the feedlot, what are they going to tell me? What's some guesses? One guess. What are they going to say? What do they want to improve? Bill, what do you think?
Meat efficiency.
You're a dairy guy. That's why you don't know the right answer. They're going to say average daily gain. We won on those closeout sheets. Man, I wanted to get 0.2 more average daily gain. But Bill, because he was smarter than me and he went into dairy, would know is what's most important, feed efficiency or average daily gain in those cattle. And it's amazing the people you can talk to and they'll argue with you on that. Average daily gain really only, the cattle obviously have to gain something, but the only thing you gain on cattle, on average daily gain, is really interest charge and yardage costs in the cattle, right? Feed efficiency is where I really make my dollars and cents. So I don't golf, but I like the golf phrase. You drive for show and you putt for dough. Feed efficiency is the putting part for beef production. Now the other question I have for the dairy, because I don't spend as much time in the dairy, is how many people that work with dairy cattle sit and worry about milk efficiency numbers? Bill, how many?
Not
Bill says not many. So that's the whole point of my talk. We've had, the previous talks were excellent, far above my head in terms of some of the amino acid work and its impact on physiology, biology of the animal, what have you. But when we're done over these next few minutes, the thing I'd like to challenge you to think about is milk efficiency and using that as a diagnostic tool for how well are these cows doing, or really, how well do I have this diet formulated for what the cows are able to do. So let's see. All right. So we have a real simple chemical equation going on. We're going to provide energy. We don't care whether that's fiber or that's starch. It's energy or fat. We have energy. We're going to put some amino acids with it. How many people think there's a metabolizable protein requirement for dairy cattle? Now, I can tell beef groups there is no such thing as a protein requirement for beef cattle. And that has gotten me the closest to getting into a fight that I've ever gotten into. And what it makes you do is run really quick, because I don't fight anymore, I run. But I can tell you there is no such thing as a protein or metabolizable protein requirement. No animal has a protein or metabolizable protein requirement. I think that was another theme up here today you saw in the talks as we're talking about amino acids to the animal. But these two things have to go together, and what we get out of that is this fluid product that's got sugar, protein, and fat in it. And what we're wanting to do is to use as few of these to make as much of this as we possibly can, and that's milk efficiency. Right? So the question then becomes what is the potential efficiency of this beast, and then how do we feed her to where we achieve that? So the relationship of milk production and amino acid requirement, being a beef person, was kind of like the Super Bowl. I watched the very end of the Super Bowl. Some people said, Monty, are you going to boycott watching NFL games? And I said, you bet I am. Like I had a stance. And they said, did you used to watch it? And I said, no, I never did watch NFL games. But I could be part of the movement, right, in doing that. The point I want to make to that is there's some differences, I think, in opinion of how people equate amino acid requirements in dairy cattle. I don't really want to argue about that as long as you agree with me. But what I did was in this, and this really comes off of, I think, what NRC's compiled in other places, is look at maintenance requirements for amino acids. That, I think, is pretty well done. And then you look at really the amino acid profile of the milk. That's ultimately, in terms of mass, what most of the amino acids have to be. So when you look at this, the way I calculate amino acid requirements, it's really maintenance of the animal, what's used for the milk. That dairy cow gains enough weight, I don't worry about assigning that to it. All that would be probably a better thing to do. But as an example, at 100 pounds of milk, I would estimate 202 grams of lysine, 56 methionine, and 74 grams of histidine. Now, all this graph I really want to point out is, as we produce more milk, we need more amino acids. Anybody disagree with that? Okay, that's an IQ test. That's not a question, right? And the point being is, if I've got enough energy to produce 100 pounds of milk, but I don't have enough amino acids to produce 100 pounds of milk, is that cow going to produce 100 pounds of milk? The answer is no, not unless she overeats diet. Not unless she overeats diet to get to that level of amino acid intake. We can go to rodent studies, we can go to poultry studies, and we can go to swine studies. And all those critters, if we feed them a diet that is deficient in amino acid, they will overeat energy to get the amino acids they need for whatever that set point of growth or performance is. It makes sense to you? So now what I'm wanting to do is to make a case that this cow, and I think we see the same thing, or it's how I explain it in cattle, steers anyway, growing cattle, is that animal will overeat to meet a set point of growth performance that's in its genes or it's physiologically set up to do, and it's going to quit eating either when it can't eat anymore, when it's met the amino acids, or it's met the energy. And whichever one of those are limiting is what's going to determine that. Same thing on energy then. This is simply NEM and NEL. I assume that NEM and NEL is used at the same efficiency because I don't like math all that much, so that makes it simple for me. So I have a maintenance requirement for a cow. As milk production increases, there's more energy, and so then I get the total, and the total amount of energy simply is a combination of those two. And so the beginning of the thesis I'd like to make is that energy will limit milk production. I can't get more milk out of that cow than what she's taken in. Now there is the peak lactation, transition, and negative energy balance, understand that. But at the end of the day, over that lactation, from an accounting standpoint, I can't get more milk out of that cow than what I've put into her, all right? So this sets what her production potential is going to be, I'd like to make a case that the amino acids are going to limit how efficient she is at taking that energy and producing that into milk, okay? So two things going on here. Energy drives the system. Water is most important. Cells have got to have energy. Amino acids are what we can influence now to change efficiency. Relationship of milk efficiency to energy density. Depending on how dense that diet is, and I did a range here of just over 1 megacals to 2.4 or something like that megacals. The more energy dense I make that diet, the more efficient biologically that cow can be. And this graph is based off of 92 pounds of milk, 1,600 pound cow, and here's the components. And I was sweating back there. I looked up my slides because the one question said 3 or greater, and I thought, man, we just did make that. I was happy about that. That's a joke in case you didn't catch that. So anyway, the point I want to make here is what happens with energy and its relationship to efficiency. And why do we have minimum NDF levels in the diet? All of that maximize forage digestibility. We want to maximize the energy that cow eats in that diet, right? If we look at dollars and cents, this is 145 bucks a ton, 62 dry matter, 92 pounds of milk, and this is then the milk efficiency. So if I start up here at 1.2, probably out of the range where most dairies are at, and I end up here at 2.2, really skirts on the edge of what biologically is impossible, so I've tried to get the range in there. But if I look at 1.4, and on that diet, that's giving me, what, $7.50 a day in diet cost. And if that cow could actually do 180, that's $6 a day. So if I don't have to change the diet cost any, but I can make that cow more efficient, I've improved the amount of money that goes into that cow every day, right? Or reduces the amount of money that goes into that cow every day. So we do this all the time in dairies. We forage digestibility, minimum fiber levels so we can put more grain, more starch, higher energy in the diet, fat inclusion, rumen modifiers, a whole list of things that we do in that diet, or what we do for the ingredients in diet, to increase milk efficiency in the diet. So I'd just like to present, or let us think about using milk efficiency as a diagnostic tool to compare production against production potential of a cow. If a dairy is at 1.4 and it can be at 1.8, nobody can argue that wouldn't be necessarily a good thing to get that herd there, unless what? Unless the cost of feed goes up so much it's no longer profitable, right? So I'm going to make the whole argument in the rest of my speech about milk efficiency, but ultimately it's what cost of milk production is the most important thing. All right, so the other thing I think setting this up is the earlier slide, we get energy and amino acids from the diet. If amino acids are deficient, then we have to use body tissue to make those amino acids. And that happens pretty thoroughly. I remember I was in a dairy judging team as an undergrad, and we went by one dairy. And so the guy who owned the dairy took us out there. And the coach was trying to get us to look at everything, mammary, suspension, all that stuff. And the guy who owned the dairy, all he cared about, he took every one of us. We'd go around the back of every cow he had on that in his barn, and we had to look at the thighs. And he said, this cow right here, she's going. And we said, why she's going? He said, because look at her legs. Her thighs are so thick she can't be milking. What's her records? I don't know, but look at her thighs. They're so thick she's going to be gone. And the whole thing is body, so we're going to lose body composition when they milk, right? We expect that. But the point being is, how much body composition or tissue do we want to lose? The other thing that's kind of interesting with one of the speakers today is, if you look at long-term starvation, I think this work was done with some dairy cattle, I think at Cornell. Long-term starvation, you get into 48 hours of starvation, you take protein, you get amino acids from protein or muscle like crazy. Just that's where it all comes from. So the idea, I think, is it's given enough time for the fatty acids and all that kind of stuff to come into play so they can provide energy. The point I want to make is, if we get out to an extended lactation, we don't have these amino acids, right? Body tissue gets regulated where that animal is only going to give up so much. As a prof I had one time said, you may be starving, but you want to be able to run away from a tiger as long as possible because food might be just around the corner the next day, right? So we regulate how much this animal can be put in, how much body tissue the animal can lose. If that happens, that means then we've only got a limited amount of amino acids that we're going to be able to submit to or use for lactation. If I'm losing body tissue here, what happens to the chances or the likelihood of that animal being able to breed back? Goes down, right? So a couple of earlier speakers talked about, I think it was Jessica talking about reproduction stuff, and I think there's a link there. All right, so these are 3 production diets that I've got to look at and either hopefully will or have played with some. 70, these are production records, 77 pounds of milk, 87.91, lactose, fat, and protein on those different diets. And then what we do is look at how we go about calculating amino acid supply and requirement. First diet, 5 grams short in methionine, 20 on lysine, okay on histidine, 10 grams short in methionine, 68, 13 short on histidine. I don't show it in this diet, but it was also short in leucine as well. In this diet, it was only short in 23 grams of lysine. Now, I took this diet because it's on the high end of the amount of lysine. And if you compute tissue loss and what's estimated in terms of how much amino acids we could get from body loss that these cows will submit, 68's on the upper end, but it's within that realm of what would be physiological possible. The thing that's interesting is most of these diets that I've run, whenever I do that, these cows all kind of sort out about where you think, well, okay, it makes sense they could get those amino acids from tissue. That's going to become important in a second. Now, what I think is really interesting about this is these are their production numbers. And then this is where we're at in amino acids. So all of these cows are short on at least 1 or more amino acids. It's within the range of what they can lose over time in from body condition, but 12 megacals excess here, this is NEM, 12 megacals excess, 4 megacals excess, and 7 megacals excess. The way we looked at that in beef was if we had more energy consumed by the calves than what they were using for growth, that meant that was the amount of energy I had that could either go for greater growth, amino acids were right, or if the amino acids were right, that much less intake in the calves. Typically what happens in calves in the feedlot is they overeat. So if you balance that diet for amino acids, all that happens is those calves reduce intake, the level of gain stays about where it was at, right? Makes sense. It's just like adding an ionophore or something that improves metabolizable energy. The milk efficiency on those cows, 1.4, 1.6, and 1.7. And if you look what the milk efficiency potential was based upon the NEM of that diet, a 1.9, 1.7, and a 1.8, and all these diets ran over 16% on crude protein. All right, now I want to go to a beef example to kind of prove that point and then come back to a dairy study that we did. Actually, it was the last slide that Jessica had shown in her talk at Penn State. The diet that was being fed in this lot was 28 yearlings, 34 wheat, 36 on distiller, 17 corn, some syrup, alfalfa, hay, tallow, and 0.5% urea. What we did was we changed these 3 ingredients. We had to bring in some Agipro to get the lysine balanced. This original diet had an EE ratio of 1.36. That meant that those calves were eating 1.36 what they needed. They were eating 1.36 times compared to what they needed for that level of growth. So they were overeating energy, but we estimated they were only at 102% of the lysine requirement. So we had to change this diet. When we did, because to make the amino acids balance, we changed these things, added lysine, also had to balance for arginine in that diet. When we did, we increased feed costs per head by about $2 per head, increased final weight of the calf, average daily gain and feed to gain was a bit improved, and kind of where the dollars came out was carcass weight was greater, gave us about a $24 advantage in carcass value in those cattle. Typically, and I've got ribeye area up here, typically the 2 things we see in cattle, growing cattle, when we adjust the amino acids are the heavier carcass weight, so an improvement in dressing percent, if not an improvement in weight as well. Ribeye area about a ½ inch bigger, and we'll also see a decrease in yield grade. So when we go into larger loads of calves, what we tend to see is if they had a yield grade 3.2, the yield grade goes down to 2.8. That's really nice if we can break that 3.2 division there and get a premium for it. But anyway, a big thing here, end result, is what growth does to carcass value. We did a similar study. This was a diet that was heavy in corn and corn silage. It was on a commercial lot. They fed a couple of pens, balanced for amino acids, or we balanced the diet that they were feeding. Gain, we got more gain off of those cattle, spent about $4 to $5 more per ton of diet, but we had a nice improvement in average daily gain. In this particular example, we really got an improvement in feed to gain. So it made an advantage in terms of feeding those cattle. Dressing percent went up on the carcass and made $44 difference or something like that in the profit of those cattle. So we've seen this approach, if you will, work in dairy cattle. Now, on the dairy study that we did, and not having worked in dairy a lot, I found this extremely interesting. So we had a 131 pounds as-fed intake. This diet is, I think, like 52% dry matter where they were feeding. 92 pounds of milk, 3.7 fat. Sorry about the protein. We got close to 3. It's not my fault, it's somebody else's diet. Lactose, somatic cells, dollars per hundredweight, and then dollars per day in terms of on that the milk, I think, calculate. I think this was $21 milk or something like that. I can't remember. Not too bad in numbers, but when we went in, we balanced the diet. So what we thought was, on this diet, and it had been balanced for amino acids using a different program. The thought we had was, it's just like cattle, or just like growing calves. These dairy cows have figured out how to do everything they can to make milk. So I give them a diet, the diet's not right, but they're going to correct it, and they're going to make all the milk they can. That's what I'm thinking, right? So we go and approach this diet, okay, they can make 92 pounds of milk. We're going to bring the amino acids up to where it meets that 92 pound of milk production need, but intake is going to come down on those cows. What happened was milk went up 5 pounds, intake only dropped really a pound of dry matter. So not much change. Milk production went up. We lost 1/10 on fat, increased 1/10 on protein. Those weren't significant. And wound up, I think it cost 40 cents a day to do that, and the net, the amount of milk we got back was $1.40 or something like that. So the net was 60 cents or something like that per cow per day. What was interesting is when we looked at the production of those cows, this was almost a 40-day lactation. I think they started about 120 days in milk, if our memory's correct. Intake was pretty quick to where we got this reduced level of intake, but out of day 14 or whatever it was here, we saw separation to where the cows that got the balanced diet then started producing more milk. The thing I thought was interesting is about that, the cow didn't say she was done milking. The cow said I was completely wrong in the assumption I made about what she could do. I interpret this data as saying that cow made more milk until she got the same point that she was limiting lysine. So when we formulated or looked at the diets, the control diet, we estimated that cow was 23 grams short in lysine. So that was one of the things we tried to make it meet in that diet. So we added that much lysine, if you will, back into the diet. When we gave that to her, she increased milk production up to the same point she was limiting in the control diet. Now I don't know how accurate 23 grams is, but what I do feel fairly confident about is the way we were estimating this, that cow simply went to the place she could go to until the same mass of amino acid was limiting her again. So this is those 3 diets I showed earlier. This is 91 pounds of milk, 7 megacals NEM excess, and this is where that diet worked out at with lysine, but the only one thing that's sufficient. If we make 91 pounds of milk and we bring this megacal excess to 0, so this cow reduces intake, or we feed her less, we've got a deficit now of lysine and histidine and leucine. And so we've got to come up with this many grams of these amino acids if we're going to improve the milk efficiency of this cow that's on 91 pounds. Now, the art of that is, if we give her that in the diet, is she going to stay at 91 pounds, or is she going to want to eat more? And that's been kind of an intriguing thing to me. And next graph after this, I'll talk about a dairy producer we've tried that at. So in conclusion, milk efficiency is a diagnostic for diet performance. So that's, I think about giving these talks when we come to the conferences, I think it's important. We have one idea that we get each time we do this that we take home and we think about, right? So whether you use it or not, it's up to you, but I'd like to make a challenge to look at milk efficiency and use that as a diagnostic for diet performance, really. Probably where your amino acids are at. Milk production potential is set by energy intake of the cow. Maximizing efficiency of energy used for milk production is dependent upon amino acid supply meeting amino acid requirement. So I think energy and amino acids, just as Louise showed in the first slide, you've got to look at amino acids relative to energy to get that balance right. And then in diets evaluated for a majority of milk production was determined by amino acid nutrition and not energy intake, like the 3 diets that I showed you. So the thing that I like to think about is we have energy and amino acids that go into this cow. We have to get milk, but we also have to repair body tissue and get successful reproduction in that cow. So we can't look at it so much as tissue going into the cow, but as rather what we have to feed to maintain her tissue. There is a dairy that's close to Columbia, where I used to live at, and the thing they found I thought was pretty interesting. We came up with their diet and we balanced it for amino acids. And now all of you will find this extremely interesting. You won't believe it that they would do this. Randy, this is a Missouri thing. But whenever milk went down, they tried to do things to cheapen their diet. Doesn't happen down here, does it?
No, not at all.
You guys don't have to worry about that, right? But in Missouri, we do. Well, anyway, Nate, and what was interesting is Nate said whenever they dropped lysine in the diet, they lost milk and protein. Whenever they dropped methionine, they dropped fat. And the other thing I thought was pretty decent is they're running a 44% first service conception rate on their cows when they've been using this amino acid diet that's been balanced, and they're running around a 1.9 or higher, 1.9 on the herd, I think, higher than that on the high-producing cows in terms of milk efficiency. And then kind of the thing to leave with, the last slide, and just go back to this relationship of energy and milk efficiency. Know where your energy's at, and then where milk efficiency should be. And what's the difference between those two? And the examples I use here is 1.9 and 1.5. There's, what is that, $1.20 or $1.10 that you have room for in that diet. So if you can make that cow more efficient and it costs you less than what that advantage is, it's kind of a no-brainer, right? It's something to pursue. And milk efficiency, I look at that as milk production over dry matter intake. It would give me a great charge if you take this out and visit with people and you get in a fight over, and that's cattle don't have a crude protein or metabolizable protein requirement. And the one thing I got in coming down here, leaving 27-degree weather to come down here, I got to thinking about is pig and the poultry folks. They go into the heat of the summer. What do they do to protein level in the diet? They bump it. Intake goes down. They want to maintain lean growth, so what do they do to the amino acids in the diet? They bump it. And Bill, I don't know some of the others, I don't know if Jose and stuff, I don't know if you've seen this or not. And I couldn't think offhand coming down here any work, but what happens if we go into these cows in the environment down here and we get this amino acid right, we get more milk out of them, but we keep intake down? What's that going to do to heat stress in these cows? I don't know if it's, I'd be interested if people have done that, or later on or whatever. I'd sure be interested in knowing about that. But to me, it's a question mark and something that may have some potential. Any questions? That's it. And I am like Jennifer. I do stand in the way of lunch.
So were you saying that when she stopped producing on that one slide, she went back to being negative 23 grams on the lysine?
Yep. Yeah, so Randy's question was, in the dairy production study we did, where did she wind up when she went to her 5 pounds more milk, right? She went mathematically right back to the same point she was limiting before. Now, like I said, I'm not so much worried about the 23 grams being a static number, but the way I interpret that, Randy, is she went right back to the point of what she could grab from the diet and what she could grab from her body. And she just used the additional we put in the diet, she used to make milk out of.
So whatever's limiting is going to be there step after step after
step. Yeah. Now, the other thing that's interesting, I didn't say, the producer that we played around with this, he was willing to do some of this stuff. And you know, if you get into this and you get 100 pounds of milk, you're 220, 240 grams of lysine. And it's interesting, the dairy consultants I've visited with, I've had the range from one saying, I don't even worry about amino acids, to one that said, he said, well, actually, I'm doing he was doing 250 grams of lysine. And he calculated milk efficiency, and he was at 1.98. And now Nate called one day, and with the dairy that we were working with, and he said, I think I've got problems. And I said, what's the problems? He said, well, I don't like the way the manure is. I'm getting close to acidosis. So it was a 30-minute conversation. We were trying to figure things out, you know. And finally I said, Nate, what are they eating? And he said, well, this many pounds of dry matter. And I thought, and I said, Nate, that's like 4.5% of body weight. He said, yeah, they just won't quit eating. So one thing that's interesting, and why I was so intrigued about that data is, I wonder how much of the intake regulation ability, satiety, we've bred out of these cows over time because we've asked them to do. So Nate gets his diet right, these cows are just taking off. And I told Nate, I said, well, I bring them back to 3.6% of body weight, let them plane out, and then if you want to go up with them, do. But it's the whole point of that just being what these cows can do. It's kind of like on the beef thing. You see some of these calves perform. People who've watched calves their whole life won't believe they could do that, right? Same thing on dairy cow. What these cows can do is just it's something. Yep. Back, Patty.
We have a question now.
Thank you for the nice presentation. My name is Ali Asnana. I'm a graduate student in Animal Science Department, University of Florida. My question is related to the heat stress. As you mentioned that heat stress affects the intake of the animal. If we remove that factor, does heat stress itself affect the utilization of the amino acid and energy within the body?
You always know, if someone says it was a nice presentation, it's going to be like a question you can't answer. So where was the talk before mine? Where's he at? Yeah, actually for you and your oxidative stress, wasn't it, or not?
Can you repeat that question?
So he was drinking coffee, so he doesn't even know what you said.
Oh, but that's heat stress. It's not oxidative stress.
So see, I told you it's a hard question.
Yeah.
So let me take a stab at it, right? So the question was, does heat stress do something independent of reduced feed intake on amino acid nutrition? Was that the question? Yeah, I don't know. What I don't know enough about is the physiology of so if we come down here, for example, the expectation is a lot of these animals in utero and stuff, if they had the same thing, they got the heat shock proteins and all the physiology that that goes into effect that, right? So I'm completely ignorant in how that physiology is going to change nutrient demands of the animal. But to say something isn't different, because we know they perform different, right? I would expect there is something going on there that's going to change amino acid nutrient nutrition, if you will. So I would think there would be, but as to having a guess, I have no guess as to how that would go. The closest thing I can think of, if we take animals, and we've done a lot with residual feed intake and metabolic efficiency. And so if we have an animal that's inefficient, okay, if I increase the amino acids to about 1.2, the required level, that animal will have a feed efficiency, feed to gain, very similar to an animal's average in feed efficiency to very good in feed efficiency. Now the assumption I make, I don't know if this is true or not, the assumption I make is that animal, because it's got to cycle through so much more carbon to get its energy ATP refilled, that it's using some of those amino acids for that purpose. So it doesn't have them to go to enzymes, protein synthesis and all that stuff, right? So if I take that model, I know those two animals have a different requirement for amino acids to maximize performance efficiency. So if an animal now is adapted, truly has been adapted or whatever, to a heat-stressed environment, I wouldn't be a bit surprised if the same thing isn't occurring, but I don't know the answer to that. Best I can do. I tried to punt it, but it didn't work.
Unfortunately, I think that's all the time we have for questions. Okay, one more.
Just don't say it was a nice presentation.
Nice presentation.
So, how often do you have to do feed analyses to know your amino acid profile on those diets, and if that potentially has any impact on the final price of your diet? And then if you see some reluctance from the producers to adopt these because they have to feed analysis more often?
Yeah, so let me distill those questions down and go through them. I want to start with the first, and let's limit this to beef, because that's where we've done most of our stuff at, right? And on the resistance of beef producers to this. And I think your question was, do I develop some resistance, or do I see some resistance to beef producers? No, I see complete resistance by beef producers to doing this, right? And it's really more of, just not to be too blunt about it, but frankly, understanding there is no protein requirement, it's an amino acid requirement, right? And the other thing is, we don't have enough data out there that shows there is a response, right? Now, what we do is, I like to hold on to biology. I had a friend of mine that was a physicist, and he said, I don't know how you guys in biology ever figure anything out, because your controls are so poor. The more data analysis you have, the better it's going to be, okay, without question. Most of the stuff we do, though, is if we go and use tabular, like feed library data, and it's very staple commodity type stuff, right? Distillers grains, corn, soybean meal, that sort of thing. We'll get really close just using feed tabular values. So in terms of how often we do it, the most often in a perfect world would be each load of ingredient you get in to do it on that. I think we have success not having it that often. Now, if it's an ingredient, things like corn syrup or distiller solubles, that there's not much information you'll get on that, so that requires more, and that would be some resistance, I think. But the two things we do is we've had a fair amount of success, I think, in being able to use feed libraries that are published if you don't have the data. And then on beef, we make one formulation. We've tried phase feeding and haven't seen a lot of benefit in cheapening up the diet at the end, because we don't have as much need for amino acids. And on lactation diets, that might be different. One of the biggest problems we have in the feedlot is if you have a 80,000 head feedlot, how do you get the feed truck driver to spot feed different pens? That's pretty hard to do, and they're very resistant to that, right? So, long-winded way around of saying that if we're 80-90% of the way there that we get most of the benefit. And I think we can do that with not being too laborious on feedstuff analysis. Now, it hurts me saying not to get feedstuff analysis because I want all kinds of it right, but it works in reality. Yep. That it, Hero?
Thank you very much, Dr. Kerley. One more hand for all